All right, welcome everybody to the Lower Columbia Amateur Radio Club presentation night. I'm Rickman KJ7OX, and we're going to cover some subject matter tonight. There's 3 subjects that I'm going to try to compress into an hour, and we'll get very quickly right into it. The main focus of this discussion is an article I stumbled across online from an earlier submission to QST magazine called a gain antenna for 28 megahertz. This particular antenna is a loop antenna for HF. It can be scaled up to VHF. It can also be scaled down to lower bands. So this particular one is designed for 10 meters. And I'm not going to read the whole article, but I can make that available to be shared. And it's also on my QRZ website. Part of it is. So if we look at our loop theory, a square loop is the typical loop. It can be parallel to the ground, horizontally oriented, or it can also be vertically oriented. You can have a reflector behind it or a director in front of it and make it directional. In this case, it's going to be bidirectional, very similar to a dipole, but with a wider pattern and more gain, which is important. So a square loop is right around 110, 112 ohms impedance, so it's not a good match for a 50 ohm transceiver. So you have to transform it. And the 2 ways that we do that typically is with a Ballon transformer or with a quarter wave matching stub, which would be a quarter wave on 10 meters of 75 ohm, which provides 50 ohms at the end of that matching stub. That's what the transceiver wants to see, is 50 ohms. So you can change the shape of a loop and get different results. And so in this article we're talking about a rectangle shape. And so the rectangle shape in this case is vertically oriented. It's horizontally polarized because it's fed in the center at the base of this antenna. It's fed like a dipole. And what this does, when you squeeze a loop narrow and then elongate it by a margin of 2 to 1, it gives you 50 ohm direct feed with no transformation. And that's really important. It simplifies the whole process. And I checked it with my rig expert analyzer and I got 48 ohms and change, which is close enough. And I think my SWR, when I finally arrived where I wanted to be, was at 28.600, about a 1.0 to 1. And so that's high enough in the 10 meter band, just into the general portion, to where you can make those excursions up the band or lower in the band and cover a great area. Now if you want to get all the way up into 10 meter FM, the antenna works fine, but you need to probably use a tuner because no antenna really covers all bands all the time. Some get pretty close. We'll talk about that later too. So in this article, it has some details, which again I'll make available for those that want it, or you can go to the web page, and the name of it would be a gain antenna for 28 megahertz, just to get that out again. So you can search that up and you can read about it. There's also another web page called Practical Antennas, which goes into great detail about the same antenna with dimensions for scaling up and scaling down for different bands. So this is a single band antenna, but you can make it a dual band. You can put one loop inside of another. And the only caveat to that is there can be some interaction, so it might change some of the lengths of the loop, each loop slightly. But to keep things simple, we're going to make a single band loop. And so just to give you an idea how successful it's been to me since October, I'm looking at my QRZ webpage right now, and I'm going to go up to my logbook, and I've only begun electronically logging since the early middle portion of October. And you'll see that my QSO count is 756 QSOs since about October 10th when I started logging. About 98% of this is on 10 meters. That's how active 10 meters has been. Wide open. And it's only getting better. And so there's reasons why this is successful. Obviously, location, location, location. That can be a huge thing for people if you live in a really noisy environment. Not much you can do about that. But some antennas can help. And so that's just the QRZ, and that's good because antennas can really help out. So for those that are here looking on the monitor, this is the page, and this is what created the interest to begin with. It was a submission to QST. The way it's written tells me it's probably 80s or 90s, and we can make copies. The copy machine works, and you guys can take more copies if you want with you. And I want to give full credit to the guy that wrote this article. His name is Brian Beasley, K6 Sierra Tango, Italy. I don't see a date, but it was submitted, contributed to QST by him, so I want to make sure that he gets the credit for this submission. And it's a great design, and I use it, and I really enjoy it, and I hope you guys will build it. So let me move on to how I built it. So the easiest thing is to just start with the shape. Okay, I know it's not very big, but you kind of get the idea. It's a rectangle. So how do we get to the shape? You start with the formula for a loop, which is 1005. So 1005 divided by the frequency gives you 30, in my case, 35 feet in circumference. Okay? So now you just squeeze it to a 2-to-1 shape, which in this case is 6 feet across the top, 6 feet across the bottom, and 11.5 feet up both sides. You do the math, you come out to 35 feet in circumference. And the two little X's at the bottom represent the feed point. You feed it like a dipole. So the center conductor of the coax goes to one side, the ground goes to the other side. Yes, it is a DC short. That's okay. We transmit in alternating current. It's also a benefit that it's DC grounded because, in my case, I have my shield grounded before it comes in the radio room to a ground stake, so it does help to bleed off any trash that might come through. And I do have a balun, a choke, at the feed point, which in this next image here, or the previous image, I'm going to show you what that's for. Let me come back to this image here in the article. You see that there is a representative picture of 3 turns of coax at the feed point. That's very band specific. So for 10 meters, around 28 megs, 3 turns of your coax at about 1 foot in diameter is going to give you about 600 ohms of impedance, thereabouts. And the whole purpose for that, there's 2 reasons for that. It helps divorce the shield from the antenna, so it doesn't skew the pattern of the antenna. It also helps promote balance for the antenna. Keeps common mode from coming back down the coax and hitting your radio, creating other interference and other noise issues. So instead of the 3 turns, I decided to use 6 snap-on beads, which are a recipe of mix 31. And you snap it on, and that provides, I have about 1200 ohms of choking. So mix 31 common mode beads at 28 megacycles are about 200 ohms each. So 6 times 2, 1200 ohms of choking. Does it work? I don't know, but I'm going to do it. It's always recommended. I didn't have any issues before with common mode or any problems, but I wanted to add it just to be on the safe side. Okay, so we'll get into the construction. This next image up here, you'll see the horizontal pieces look a little bit fatter than the vertical pieces. And you'll see now I have a box kind of at the bottom, and we'll get to that in a minute. I'm going to go to the whiteboard here real quick. This isn't going to be to scale, but it is a construction method. So what I use is 1/2-inch gray PVC electrical conduit. So just picture a conduit on the top, conduit on the bottom. And in this box here is where you make your termination, where I made my termination. So I have an SO239 chassis connector. So just like the plug-in on the back of your transceiver, I wanted to make it plug and play. And this would be the center pin. So essentially the wire that's 35 feet long gets soldered to the center pin, comes out the conduit, through the upper one, back down again, through here, and this has a ring terminal soldered to it, and it goes to the ground side. That's what that does. So that creates the loop. And your coax plugs in here, and you can put your beads, or you can put 2 or 3 wraps of coax, about 1 foot in diameter or so. But that's the basic construction shape. And I had all the parts except for the gray conduit, and I think that was 16, 18 bucks for a couple of sticks. Pretty cheap. And I got gray because it's UV stable. Water pipe PVC is not. It'll fall apart in a few years. Gray electrical EMT PVC. Nope, it just hangs. Yeah, it's totally gravity. So, good question. I'm glad you brought that up. So, my coax is RG213, so it's about 45 feet off the ground, 40 feet, so almost 12 meters high. And so, it creates some weight. And I didn't want to pull this lower spreader down with the weight of that. I wanted to try to maintain a shape. So I basically just, created a loop here of black Dacron rope. You can get that at HRO, DX Engineering. It's UV stable rope. And I ran that rope from here to the top, connected it, and then that goes over the tree limb and then down. So that supports it all the way through and then maintains a shape. And I've got a photograph of that here too, installed. Any questions so far? Okay. And the other thing I had to do too, because there can be fading, they call QSB, QRN, and signals can be up and down depending on the time of the day, the band conditions, etc., etc. When I first put this up, I experienced a lot of fading. A couple days go by and I didn't realize why I was having so much fading trouble. So I go outside and I look up in the tree and the antenna's not pointing east anymore, it's pointing south. It's going like this in the wind, turning. So what I ended up doing is I put a tag line off one end down to a tree so that it doesn't go more than a few inches. So that took care of that, so bear in mind. Yes?
The rope goes to the tree.
Yep.
Okay, what's holding the other end of it up from falling down on the other side?
Over here?
What's that attached to?
So the rope is connected to this lower piece of PVC and it's connected to this top piece of PVC. It's all balanced, so it's not tipping. It's perfectly balanced in this case. But if I was to pull on this tag line, then it would kind of go like this and become misshapen. So you could put 2 tag lines with equal pressure and keep it more stable.
But you don't have a lot of tension or anything.
No. Almost the weight of the rope by itself. Yeah. Real simple. So the box in the bottom, in electrical terms, they have a lot of different names. They have LBs, LCs, different things like that. It's not a junction box. But I got a screen grab of one. That's called an LC, which means center. So out one end and continues through the other. And so what I did, where my mouse is right here, I drilled that out with a step drill bit, which is a conical shaped bit, so the more you drill, the bigger the hole. And then the SO239 got attached to that for a direct plug-in. I also did put a drain hole on both sides of that, in case any water comes down, kind of works its way down, it'll have some place to go. Just little things like that to keep in mind. Let's talk about some differences really quick between the square loop and the rectangle loop. Quick drawing I did, and the angle of radiation depending on height above the ground. And the first half wave off the ground with any antenna is the most meaningful. Everything higher just gets better. But there are diminished returns if you go too high. So a square loop, a minimum a half wave off the ground or slightly more, is going to have, now this is in the vertical plane like this, straight up and down, is going to have about a 25-degree angle of takeoff. That's not bad. That's on par with the dipole, pretty close. And you'll see here where it says the feed point impedance is 112 ohms. They may not look like it, but just picture, for the sake of discussion, that they're both 35 feet in circumference, okay? Just one's square and one's rectangular. And so in this example, a square loop has a bit over 1 dB gain over a dipole. It's not very substantial. You would think, well, why would I want to go through all this trouble if it's not much better than a dipole? And it's not much better than a dipole. That's a fact. But it's a lot quieter than a dipole. And its 90-degree rejection, which means off the ends, is quieter than a dipole. So when you go into minus numbers, it's about minus 24 dB. So it gets pretty deaf off the end, which a dipole does too. And you can use that as an advantage. That's a great tool. You can actually turn it if you wanted to and block somebody else out that's maybe an offending signal. So, back to the documentation on this. A 1.1 dB gain amount over a dipole equals, I believe it's a 29% increase in power over a dipole. 29%. You think, okay, well, that's not bad, that's something. And it is. Considering a dipole is 0. But when you stretch this antenna into a vertical rectangle, it changes to a 62% increase in power over a dipole. That's over 2 dB gain. So we've talked about the direct feed. You change the shape of it, you get 50 ohms. That's item number 1. Now, you have more gain over a dipole. That's item number 2. There's one more component. And this other component is the angle of takeoff. And so if you look at these two examples, the upper one has an arrow that's about 25 degrees. The lower one has one that's about 12 degrees. Most of your DX that comes in from around the world comes in anywhere from about 3 degrees to about 7 degrees. We can't always transmit that low of takeoff angle, but that's what we're going to receive. So anytime you can get as low as you possibly can when you transmit out, that's better. This antenna gives you between 10 and 12 degrees angle of takeoff. It's a great performing antenna. So I modeled this antenna using a modeling software program called MMANA-GAL. And this is the model that I have. And you can see on the left of the screen here, it has that classic figure 8 sort of profile that you would see in a dipole, but with gain. 2.1, 2.2 dB above a dipole. And when I talked about the 90-degree null, it's the area that I'm going to call through the center, almost the narrow part of an hourglass here. So you can see if you're aiming in this direction up here, that's where you want to aim, either front or back, because it's bidirectional. That's where your gain is. But if anybody is stuck in the side here, another signal, they're going to be way down. Way down. And on the right, this view is if you were standing on the pavement looking into the antenna, looking through it. And this is what's most important. You'll see above it, there's very little wasted RF above the antenna. Okay? And you see the low takeoff angle. Here, for instance, is 12 degrees above the horizon. It's very low. So it's great for DX. And you'll see here at the Z, which is the ohms of impedance, comes out to be about 48 ohms. And I got the same thing, like 48 point something I got from my Rig Expert Antenna Analyzer. And so the projected SWR was supposed to be 1.5. I got 1.0 to 1 at 28.6. And that's at a bit above 10 meters off the ground. So not quite 40 feet. It would probably be exactly 1.5 if it was a half wave. So in this case, higher is better. So I also did a sort of a 3D colorized view of what the radiation would look like if we could actually see it. So it kind of looks like a flower, but again, standing on the pavement looking in through the antenna, you can see where the low takeoff angle maximum gain lobes are highlighted red. So that's a really good pattern. And if you see down here at the very bottom, this area of this little gap down here, about where my cursor is about 5 degrees. And 5 degrees is always a great low takeoff angle test case when you're trying to measure antennas in software. 5 degrees is not easy to get. You can receive it, you can't always transmit it. So always have a test at 5 degrees to see where you're at. It's okay if you're in minus numbers. Your numbers might be minus 5 dB gain. You think, well, I'm losing ground. Well, not really. It's just the number. It creates the shape that you see right now. It's kind of how that works. Okay, and so now we're going to go to another view of the 3D plot, colorized. And you can see now the shape of the antenna that I drew in here with the colorized version on each side. So this is bidirectional, like a dipole, goes in two directions. I have it oriented so that the radiation goes east, or a little bit south of east, also west. And from this particular location in the northwest, when you have it in this corner of the country, I get a wide splash across the whole lower 48 states with no nulls. And that'll be important for the next antenna we talk about here in about 5 minutes. And so I have that during the day, and then later in the afternoon I have JA, which is Japan, Asia, Asiatic Russia, Hawaii, Alaska, just pounding through the back end of this antenna. And I have a bit of dirt in the way between me and ZL and VK, which is Australia and New Zealand and the deep South Pacific Islands. But once it gets closer to the equator, it frees up again and I can work some of those islands, like Midway and other islands. And there are special events that go to Midway and other places. So that's that particular version. And here is the aerial version of the same thing now, as if you were a bird flying over the top of it. That's what it looks like. So it's a really wide pattern, and that's good. You can use a really wide antenna pattern as a tool to cover a large area. So now I'm going to show you some other parts here. These are SO239 connectors. That's what your PL259 coax connector plugs into, like in the bottom of this image right here. So direct coax plug-in. This antenna probably weighs a pound, if that, and very lightweight. You could actually take this on a what they call a squid pole or a fiberglass pole, and take it out in the woods and put it up in the air on a pole, throw it over a branch, take it portable.
What is the actual wire that you use?
I'm just using 14 gauge PVC coated UV stable wire. You get a DX Engineering for, I think it's 35 or 36 bucks for 150 feet. When I first, one second Rick, when I first put this up, I didn't want to use my good wire for testing. So I built a Frankentenna. It's a Frankenstein antenna, several bits of copper wire, some insulated, some not, different colors. It was just a wreck. And but I wanted to get the full footage. I wanted to test it out for a month or so, and if it fell apart in place, that's okay. Before I pulled a brand new clean run of wire off the spool, I wanted to test it out. It's always good to do that. So don't throw your pieces of wire away. Test away with them. Yes, Rick?
Stranded or
Either one. I'm using stranded. I think it's copper-clad steel, good antenna wire, very strong, and you know, you don't have to worry about it rusting. It's in a PVC coating anyway. The steel component just gives strength. Your signal that you transmit does not go in the wire. It's on the outside of the wire, so no problem with that. Yes, Matt.
I don't know if you were gonna cover this later, but is there a reason that you chose to have a vertical rectangle instead of a horizontal rectangle?
Yes, it's quieter because it's fed at the bottom, and for the reasons that I've outlined, performance.
Even if it was horizontal, you could still feel it.
You can do that, but you get different reactions, and you don't get the same performance because now you have more horizontal wire closer to Earth as opposed to less.
Right.
Because in the website that I'm going to share with you guys called Practical Antennas, that's the name of it, you can make different versions of this antenna, and I'll just draw one really quickly because there may be a need for you guys to, based on the limited space that you might have, to make one like this. Okay, so 50 ohms at the bottom because you have the exact same circumference. It's elongated, 50 ohms. Only requires one support to go across, and then the rope comes out the top. And this isn't going to drop or anything because the pressure of the shape of this holds that intact.
What do you use to attach the wire to the rope?
Well, you could just use zip ties.
Just zip tie?
Yeah, you can use zip ties. It's insulative, so that's fine. That's just an example of a different shape that does exactly the same thing and has very nearly the same performance.
Start with 35 feet of wire.
35 feet of wire. And if you're 12 meters, if you want to make it for 12 meters, it's probably 38 feet. You know, and there are people that have giant towers, you know, 100-foot towers, and they can probably put one of these up for 80 meters. This guy's not one of them, but they're out there. They're out there. So, and then we get to, what does it look like in the air? I don't know if you can see that. I can blow it up a little bit, but this is what it looks like in the air. And if I zoom in a little bit here, you can see at the bottom I have my choke beads that I made right next to my cursor here. Can you see those?
Yep. And that's the bottom of it.
That's the bottom of it. And since then I have two tag lines, one here and one here. Slightest amount of tension to keep it from turning. And then here's the upper spreader right here, slightly arced. And the only reason why there's a slight arc to this is because of the weight of the wire, which is just a few ounces. And that's it. And you can see the rope going up through the middle right here, which supports the weight of the coax so it doesn't pull the bottom spreader out of shape. And yeah, it looks like it's right next to a tree, and it is. Is that going to hurt anything? No. It's about 3 feet away from a big tree. Doesn't matter. I'm blowing right through it. Works good.
Where does it attach to the tree?
So what's just out of view above it is a larger branch. So that is the 10-meter loop. Part of the discussion. So any questions on that? It's really simple, really effective, has a great pattern. I can't tell you how many people tell me, how much power are you running? 100 watts. And they'll say often you're coming in 20 over, 30 over. I can't believe it. That's it.
I've got a question, and,
Yep.
and it may be something you might have a theory on.
Mm-hmm.
Years ago, I played around a lot with CB, and we built a lot of quad antennas, which was a square setup. Feeding them on the bottom, put them on a horizontal plane, you feed them from the side, it put them on a vertical plane.
That's right.
Now, have you tried anything with feeding this on the side?
I have not, but let me go to the board again really quickly because that can be done. That can be done. So just take the same rectangle and then feed it on this side. And what you have now is you have essentially two verticals in phase. Is basically how that works. The vertical polarization with very low takeoff angle. But this antenna, you can be closer to the ground. It has different performance, not quite as good as this, but different people have different antenna designs for a reason. This might do a better job for a certain reason on a certain band than the other one. That's why hams have so many different kinds of antennas, because they have to do something different.